1901, a scientist named Thomas Young performed an experiment that changed everything. It is called the double-slit experiment, and today it is considered one of the most puzzling experiments in the history of physics. In fact, many of the mysteries of quantum mechanics are rooted in this very experiment. This is actually an experiment you can try at home. Take a piece of plastic or any material that does not let light pass through. Make two narrow slits very close to each other. Then shine a laser light so that it hits both slits evenly. Even a small toy store laser will do. Most of the light from the laser will be blocked by the plastic, but the portion that passes through the two slits will fall on the wall or screen behind it. Now here is the twist. What you see on the screen is not just two bright lines behind the slits. Instead, you get a pattern of many lines. That is the strange part of the double-slit experiment. Thomas Young's original experiment in 1801 was slightly different from this. Since lasers did not exist back then, he used other methods to produce coherent light that behaves in a similar way to laser light. The materials he used were also different, but the basic idea remained the same. When he directed the light through two narrow slits, he too observed the same pattern of alternating bright and dark bands. This pattern is called the interference pattern. This interference pattern has some unique features. At the exact center, there is a bright line. On both sides of it, there are two dark lines where no light falls, and intense, and the brightness of the other bright lines gradually decreases as you move outward from the center. The real question here is, how does light, passing only through two slits, create so many lines like this? If light were just a stream of particles, this should not happen. Just like in the case of bullets, we would expect only two lines directly behind the slits. But if light behaves like a wave, then a pattern like this becomes. To understand how this pattern forms, let us take an example we are familiar with: waves on the surface of water. Imagine a tank filled with still water. Now, suppose we drop a stone on one side of the tank. Waves begin to form at the point where the stone falls and start moving toward the other side. Now imagine placing a plate with two slits in the path of these waves. Most of the wave gets blocked, but a portion of it passes through the two slits. What happens next is interesting. From each slit, a new wavefront emerges, as if the slits have become two new sources of waves. As these two wavefronts move forward, they begin to overlap. In some places, the peak of one wave adds to the peak of the other wave, and the trough of one wave adds to the trough of the other. This is called constructive interference. That is what happens here. The high points are marked with a yellow dotted line. Along this line, the high points of the two waves combine at these positions, and in between, the low points of the two waves also combine at these points. The result is a wave with higher peaks and deeper troughs, a stronger wave. This is called constructive interference. But waves can combine in another way too. If the peak of one wave meets the trough of another, they cancel each other out. This is called destructive interference. That is when along this line, the high part of one wave and the low part of the other meet and cancel, creating a region where there is no wave at all. So, in the image shown here, you can see alternating lines, some where the waves have added up, creating larger waves, and others where they have cancelled out, creating regions with no waves. And when these waves hit the back wall, they produce alternating regions, some where larger waves strike, and others where no waves reach at all. This is exactly what happens in the case of light as well. The light waves that emerge. Travel forward and hit the barrier. Most of the light is blocked, but the portion that passes through the two slits moves ahead as two new wave fronts. When these two wave fronts meet, interference occurs, just like we saw earlier. Lines of constructive interference and destructive interference are formed alternately. When these interference lines hit the back wall, the regions where constructive interference occurs appear as bright lines, and the regions with destructive interference appear as dark lines, areas where no light reaches. This is what creates the interference pattern we saw earlier. To summarize, the fact that we get an interference pattern when performing the double slit experiment is one of the strongest proofs that light behaves like a wave. And that is exactly what Thomas Young's experiment demonstrated back in 1801. It showed for the first time that light is a wave. Later, by the 1860s, James Clerk Maxwell showed that light is not just a wave, but an electromagnetic wave. And so, for nearly 100 years, the idea that light is a wave remained firmly accepted. By the early 1900s, scientists began noticing that the wave theory of light could not explain certain phenomena. In effects like black body radiation and the photoelectric effect, light did not behave like waves at all. To explain black body radiation, a scientist named Max Planck introduced a new idea in 1901, the concept of the quantum. This marked the beginning of a new branch of science known as quantum physics. Later, in 1905, Albert Einstein proposed that light is not a continuous stream of energy, but rather a stream of discrete packets of energy called photons. Using this idea, he was able to accurately explain the photoelectric effect. For this contribution, Einstein was awarded the Nobel Prize. But this raised a contradiction. The double slit experiment had already shown that light behaves like a wave. And now, Einstein's work suggested that light is also a particle. This is how the idea of dual nature emerged. The conclusion that light exhibits both wave and particle properties at the same time. This became known as wave-particle duality. As we go forward, things only become stranger. In 1924, a scientist named Louis de Broglie proposed that just like light has a dual nature, matter particles might also have wave-like properties. It is easy to accept that light, which is energy, can behave both like a wave and a particle. But electrons and protons are real matter particles. So how could they possibly have wave nature? To test this, the Davison-Germer experiment was conducted in 1927, and it showed that electrons do indeed have wave-like properties. However, a true double-slit experiment using electrons, similar to what Thomas Young had done with light, was not performed until 1961. Just like with light, a beam of electrons from an electron source was directed toward a plate with two slits. Most of the electrons hit the